In this videotape, we're going to look in detail at the types of protection used on transformers. We'll also be discussing protection for reactors and capacitor banks. Transformers are used all over the power system at all voltage levels and in sizes ranging from, say, 3 kVA up to 500 MVA. Generally, power transformers are three-phase. That is, the primary and secondary windings of each phase are wound on 3 legs of a common iron core, all immersed in the same tank of insulating oil. Single-phase transformers are also used, connected to form a 3-phase bank. Any combination of Y or delta connections can be made to give the desired voltage levels and phase relationships. Remember, with a Y delta or delta Y arrangement, the transformer is normally connected so that the high side voltage leads the corresponding low side voltage by 30 degrees. This is in accordance with IEEE standards. The advantage is that interconnection between utilities is simplified. Many transformers have 3 windings, that is, a primary, secondary, and tertiary, all wound on the same core. For example, we may have a primary of, say, 100 MVA at 138 kV, a secondary of 75 MVA at 69 kV, and a tertiary of 25 MVA at 13.8 kV. And each of these windings may be connected in Y or delta. You will recall from basic transformer theory that power in equals power out in an ideal transformer. Therefore, the sum of the secondary and tertiary MVA equals the primary MVA. The type of protection scheme used depends to a great degree upon the size and importance of the transformer in the power system. But another factor is the installation itself. Sometimes, in order to economize, the transformer is not provided with circuit breakers, hence the protection equipment must be designed with this in mind. The transformer must be protected against internal faults and through faults. Internal faults occur as a result of insulation failure, which creates a short circuit path between phases and often to the grounded iron core. The heavy fault current flowing can cause serious damage to the windings and even burn the core itself. If an internal fault does occur, the transformer must be immediately switched out of service and isolated. Differential protection provides the best protection against internal faults. And we'll be discussing this in detail in the next segment. Through faults would normally be cleared by other protective devices downstream. However, if the fault fails to clear, this could place a severe overload on the transformer. Heavy fault current flowing in the secondary winding will produce a corresponding relatively heavy current flow through the primary. For example, let's look at this delta primary Y secondary transformer. If a 3-phase short circuit occurs downstream of the secondary, heavy fault current will flow through all 3 phases of the primary winding. In the case of a phase-to-phase fault on the secondary, in this example between lines B and C, then heavy fault current will circulate in the secondary B and C phase windings, and likewise, heavy current will flow through the associated windings on the primary. And this will be in addition to phase A load current, which is still being supplied. Where there is a ground fault, in this case on line A, additional current must flow through the associated phase on the primary, like this. The result of this high fault current passing through the transformer can be mechanical and thermal damage. The high current causes physical movement of the windings, and this in turn can cause rapid breakdown of the insulation. Similarly, the insulation will deteriorate rapidly due to the high temperature resulting from high overcurrent. The thermal or current limits for operation of transformers are indicated in ANSI and IEEE standards. Copies of these standards are included in your workbook. 4 classes of transformers are categorized by size, and for each category, a curve is provided showing the thermal limit for transformers in that category. This curve indicates the allowable time of operation for different values of overload. For example, with 3 times the normal rated current, this transformer can operate for 300 seconds, that is 5 minutes, before damage will occur. If the overcurrent is at 10 times normal, then the allowable operating time is only 15 seconds. So, how can we prevent this from happening? Well, the first line of protection would be the operation of protection devices downstream in the low voltage system. In fact, the low voltage protection will probably be set to operate on a curve like this and trip the feeder breaker. You can see here that for 3 times rated current, the feeder protection will trip in 2 seconds. This is long before the thermal limit of the transformer is reached. However, backup must be provided to protect the transformer in the event the downstream feeder protection fails to operate. This is usually in the form of overcurrent protection on the primary side of the transformer. In many installations, there is no breaker installed on the primary side, and protection is provided by high voltage fuses. You'll recall that the characteristic of the high voltage fuse is similar to the time overcurrent relay. Both have an inverse time characteristic. The higher the overcurrent, the shorter the tripping time. Now, in selecting either the fuse ratings or the setting for the overcurrent relay, attention must be paid to coordination. That means protection must be provided for the transformer, which allows time for operation of downstream protection devices. Referring to the curve, it is apparent that we must choose a fuse or overcurrent protection setting that operates in this area. For any particular overcurrent value, this relay or fuse is slower in operation than the downstream feeder protection, but both operate in good time before the transformer thermal limit is reached. Let's look at a few typical arrangements. Here, the transformer feeds a bus through a secondary breaker, and the bus supplies several feeders, each with its own circuit breaker. A fault on any feeder should be cleared by the feeder protection opening the respective breaker. If this fails to open, or there is a fault, say, on the bus, then the transformer secondary breaker will open. This is set at a much higher level and slower speed than the feeder protection. If this protection fails, then the high voltage fuse on the primary should blow to protect the transformer. Another arrangement here, commonly used on distribution circuits, shows the transformer secondary connected directly to the bus, which in turn feeds several feeders through reclosers. Once again, the feeder recloser should lock out for a permanent fault. If not, the high voltage fuse on the primary should operate to protect the transformer. However, if the secondary fault level is low, the high voltage fuse may not clear. In fact, it may not even detect a low-level fault in the secondary winding. We'll be talking more about this problem later in the tape. Another arrangement here shows a circuit breaker on the primary with the secondary connected directly to a bus. Each feeder has its own circuit breaker and individual protection. The primary circuit breaker will trip for a fault in the transformer zone, or fault on the bus, or a fault on any feeder, which fails to be cleared by its own primary protection. Because of its inverse time characteristic, overcurrent protection is well suited for backup application, but for protection against internal faults, more sophisticated schemes are required, particularly on large transformers. Well, at this point, let's take a break, and then we'll come back and look at differential protection as applied to transformers. Please switch off the tape now and review this material in your workbook. You'll remember that we discussed differential relays in some detail in earlier tapes, including the function of restraint coils. We also studied the application of differential protection to generators. Generally speaking, differential protection is applied to all transformers of 10 MVA and above, and also on smaller transformers where they provide an important function in the system. When applying differential protection to transformers, certain factors that must be taken into consideration are the magnetizing inrush current, the phase shift in Y-delta connected transformers, CT connections, that is phasing, selection of CT taps, and the effect of transformer taps. As we pointed out in an earlier tape, inrush current is due to the initial energizing of the transformer. The large inrush current is high in second harmonics, and this factor is used to provide harmonic restraint to differential relays, which are used for transformer protection. The harmonic restraint unit filters out the second harmonic and uses it to restrain operation of the relay. After a few cycles, the inrush current is reduced and the second harmonic current disappears, so allowing the relay to operate as normal. With this type of differential relay, the pickup current is usually set within the range of 0.75 to 2.5 amps, with an operating time of 0.015 to 0.03 seconds. For smaller transformer banks in the sub-transmission and distribution systems, a simpler differential relay without harmonic restraint may be used. The operating element consists of an induction disc. This operates quite slowly, about 0.1 seconds, so it will not be responsive to the short-term inrush current. In yet another method for preventing tripping due to inrush, the operating coil of the differential relay is desensitized for a few milliseconds when the primary breaker is closed. Let's move on now to look at CT connections. The differential protection must compensate for any shift in phase across the transformer. This is achieved by careful connection of the CT secondaries. This action is known as phasing. If the transformer is connected delta on both primary and secondary sides, then we will normally use Y-connected CTs on both sides, as there is no 30-degree shift to correct. The CT secondaries are connected to their respective restraint coils at the differential relay. That is, line A to restraint coil A, and so on. Where the transformer is connected, grounded Y on the primary and grounded Y on the secondary, the CTs are delta connected on both sides. Why is this? Well, with Y CT connections, zero sequence currents may flow in the relay, causing unwanted tripping on through faults. Delta CT connections are safer as they eliminate zero sequence currents from the relay. Where the transformer is Y connected, the CTs should always be connected in delta. Care must be taken in connecting the secondaries so that each phase differential relay receives corresponding input from both sides of the transformer. Now let's look at phasing for the delta primary Y secondary transformer. The high voltage side operates at 138 kV line to line, while the secondary side is at 69 kV line to line. The neutral of the Y-connected secondary is grounded. Therefore, the CTs on this side of the transformer should be connected in delta, as we have just explained. Having established this, it is obvious that the CTs on the delta-connected primary must be connected in Y so as to correct for the 30-degree difference across the transformer. Of course, the CT ratios must be selected to allow for the different secondary currents resulting from Y or delta connection. It's easier to connect the Y-connected CTs to the relay first. Then make connections from the delta-connected CTs to each phase relay so that both sides correspond to the same primary line. Let's check this. First, note we have indicated the currents inside the delta-connected primary windings to be IA, IB, and IC. Looking at the primary side and remembering that it is delta-connected, we find that the line current in line A is IA minus IB. In line B, the line current is IB minus IC. And in line C, the line current is IC minus IA. Observing the polarity markings of CTs on this primary side, we see that the current flowing to the differential relay is IA minus IB in this phase, IB minus IC in phase B, and IC minus IA in this third phase. On the secondary side of the transformer, the current in each line, as this is Y connected, is IA, IB, and IC. Observing the polarity of the CTs, we see that currents passing through the CT will produce secondary currents in this direction. Remember that these CTs are connected in delta. Therefore, the secondary current at this point will be IA minus IC. But in order to compare the currents on either side of the differential relay, we must know the value of the current in the opposite direction. So this will be IC minus IA. Similarly, with the other two phases here, we have IB minus IC, and here IA minus IB. In each case, the current on either side of the differential relay corresponds to its respective line currents. Thus, the phasing is correct. Now, with load current assumed to be zero, suppose an internal ground fault occurs in phase C. With a delta Y transformer, this will cause increased current flow in primary phases B and C as shown. This in turn causes increased current flow in relays B and C. With this radial system, there is no backfeed, so there is no current flow in all secondary CTs. Thus, there is an imbalance of current flow in relays B and C, and both will operate. For an external fault, currents balance on both sides of the relay and no operation takes place. Check this and other examples in your workbook. In addition to CT phasing, we also have to pay attention to the CT ratio tap settings in the differential relay. You will remember from an earlier tape we pointed out that the CT ratio tap settings could be adjusted over a wide range in order to reduce as far as possible the difference or mismatch in the CT characteristics. In fact, this mismatch can be evaluated by comparing the difference in the ratio of high side current to low side current against the ratio of high side tap setting to the low side tap setting. That is IH over IL minus TH over TL. Let's look at our example again. We have a 50 MVA transformer, and the line voltage on the primary side is 138 kV. So the line current comes to 209 primary amps in each line. If we assume the ratio of the primary CTs to be 250 to 5, that is 50 to 1, then we have 4.18 amperes passing through the primary side restraint winding of the differential relay. On the low voltage side of the transformer, the line current is equal to 418 amps. What would be a logical CT ratio on the low voltage side? Well, as the voltage is half the line voltage on the primary side, then CT ratio would be 100 to 1. So the current in the CT secondary will be 418 divided by 100. That equals 4.18 amps. But remember, the CTs are connected in delta. Therefore, the current in the secondary restraint coil is equal to 4.18 times root 3, which equals 7.25 amps. The ratio between these two, IH divided by IL, equals 4.18 divided by 7.25 equals 0.577. Let's now look at the taps. And suppose we have the high side CT tap set at 5 and the low side tap set at 9. The ratio TH over TL equals 5 divided by 9, or 0.556. The difference between these two, that is, the mismatch, is 0.577 minus 0.556 equals 0.021. The percentage mismatch is 0.021 divided by 0.556, and that equals 3.78%. In other words, percentage mismatch equals IH over IL minus TH over TL, all divided by TH over TL, or IH over IL, whichever ratio is smallest. What would be the result if the low side tap had been set to, say, tap number 8? Here, the ratio TH over TL would equal 5 divided by 8 equals 0.625. In this case, the mismatch is a negative value, but it really doesn't matter. It is still a mismatch of 0.577 minus 0.625, or minus 0.048. The percentage mismatch equals 0.048 divided by 0.577, which equals 8.3%. Now, in both of these answers, the mismatch percentage is far less than the restraint slope, which is usually set between 20 to 40% on transformer differential protection. The CT ratios should be selected to keep this mismatch to the absolute minimum. But at the same time, the current on the CT secondary should not exceed the current ratings of either the CT or the relay restraint coils. Generally speaking, the CTs are rated at 5 amps maximum, while the restraint coils have a continuous rating of 10 amps or maybe more. Another way to ensure good performance from the CTs is to have as low a burden as possible. Preferably, individual CTs should be used to feed differential relays. When the transformer has load tap changing, the voltage ratio across the transformer can change, and with it, the percentage mismatch. The CT ratio selection should be made with the tap changer in the mid position. Suppose in our previous example, the tap changer could raise or lower the secondary voltage by 10%. On the upper tap, that would be 75.9 kV. line current in the secondary would now be 50,000 divided by root 3 times 75.9, which equals 380.3 amps. The secondary current in the restraint winding would now be 380.3 divided by 100 times root 3, or 6.58 amps. So the ratio IH to IL is now 4.18 as before, divided by 6.58, which equals 0.635. So our percentage mismatch now becomes 0.635 minus 0.556 divided by 0.556, or 14.2%. So it is still less than the restraint coil percentage differential setting, indicating that the differential protection will operate correctly throughout the upper range of tap changing. Incidentally, if you go through this exercise again for the minimum tap setting, that is a secondary voltage of 62.1 kV, you'll find that the mismatch comes out to 9%. Knowing the range of possible mismatch helps you set the percentage differential, that is, the slope of the relay. Now at this point, having established the importance of correct phasing and selection of CT ratios, we'll take a break. And then we'll come back and continue our discussion of differential protection for transformers. For now, please switch off the tape and review this material in your workbook. Continuing our discussion of transformer protection, we'll now move along to look at a more complicated transformer connection. Now, this is one with a tertiary winding. That is a Y-connected primary at 230 kV, a Y-connected secondary at 69 kV, and a delta-connected tertiary winding at 13.8 kV. The capacity of the respective windings are 65 MVA for the primary, 40 MVA for the secondary, and 25 MVA for the tertiary. The Y-connected windings in both the primary and in the secondary are grounded through their respective neutrals. Note that each external line connection is provided with its own set of CTs. This is important, as we shall see. Also, in each phase differential relay, a separate restraint coil is available for each CT connection. As we discussed in the last segment, the CTs in the Y-connected windings must be connected in delta to avoid operation on external ground faults. And as before, in order to accommodate the 30-degree phase shift, the CTs in the delta-connected tertiary must be connected in Y. Here is the three-line diagram. To determine CT and relay connections, we must carry out a phasing study. When dealing with multiple winding transformers, it's always advisable to study CT phasing in pairs of windings, considering the third winding to be at zero load. Let's start with the primary and tertiary windings. Line current IA passes through the A phase transformer primary and into the neutral. This gives us current IA this way in the CT secondary. Similarly, IB and IC pass through their respective transformer primaries and into the neutral, giving IB and IC in the CT secondaries. The resulting secondary relay current, shown by a yellow arrow, is IA minus IC. Similarly, the other secondary relay currents are IB minus IA, this green arrow, and IC minus IB, this blue arrow. Now let's look at the current flow in the tertiary CTs. The current in each phase of the tertiary winding corresponds to its primary, IA, IB, and IC. However, as the transformer is connected in delta, the line currents will be different. For example, in line A, the current this way is IA minus IC, shown by a yellow arrow. Here we have IB minus IA, the green arrow, and in this line, IC minus IB, the blue arrow. The CT secondary currents are representative of the line currents and are indicated by appropriate yellow, green, and blue arrows. These currents from the tertiary transformers are the currents leaving the relay. Having established the direction of the currents for clarity, we'll remove polarity marks. Now let's look at the current flow in the restraint coils. The secondary current IA minus IC, the yellow arrow, enters this differential relay phase A. The current leaving this phase A restraint winding is also IA minus IC. Remember, the current in the other restraint coil is 0. Therefore, the current passing through the relay operating coil must be 0. This is correct. The differential relays B and C have similar currents, and the current in their operating coils is also 0. Now, having checked the primary and tertiary windings, let's check the phasing of the CTs in the transformer's secondary. These are delta connected like the primary. Hence, like the primary, the currents from the relay are IA minus IC, IB minus IA, and IC minus IB. With balanced operating conditions, these three sets of currents cancel, and no current will flow through the operating coil. If an internal fault occurs inside the transformer, then out-of-balance currents flow in the operating coils, and the relay will trip. With the multi-winding transformer, selecting the correct CT taps and calculating the mismatch is similar to our earlier example. The essential feature is to work with one pair of windings at a time and assume the same MVA for both windings. For example, let's consider 40 MVA passing from the primary to the secondary. The line current in the primary will be 40,000 divided by √3 times 230, which equals 100.4 amps. Assuming a CT ratio of 30:1, and remembering that the CTs are delta connected, the secondary current equals 5.8 amps. On the secondary side, the current in the transformer windings will be 40,000 divided by √3 times 69, or 334.7 amps. Assuming a CT ratio of 400:5, that is 80:1, and remembering the delta connection, the CT secondary current will be 7.25 amperes going to the relay. The ratio then between IH and IL equals 5.8 divided by 7.25, or 0.8. Now, let's suppose that our taps are set on 5 and 6 respectively, giving us a tap ratio of 0.83. Our mismatch can now be calculated as 0.83 minus 0.8 divided by 0.8, which equals 3.75%. This is well within the transformer differential relay restraint setting. A similar calculation would now be made for the tertiary, using 25 MVA as the base. At times, the mismatch may be too high for good reliability, even when using the whole range of taps. In this case, it may be necessary to use auxiliary CTs in the main CT secondary circuit. In this single line diagram, you can recognize the connections to one phase of the differential relay. However, in following through the operation, it helps if we connect the other end of each CT, first for the two outer windings. If we consider the load on the third winding to be 0, we can see that there is balance here. The same secondary current passes around this circuit with no flow through the operating coil. We must remember, however, that this is a schematic, and with the CTs connected in delta, CT secondary current is not the same as relay current. CT secondary current times the square root of 3 equals relay current. Now, if there is load in the third winding, we must connect the third CT like this. Suppose we have, say, 0.6 amps in this first circuit, 0.5 in the second, and 0.1 in the tertiary. The current will flow like this, and as we can see, it still balances, and there is no flow of current through the operating coil. In studying these diagrams, usually these additional connections are left out for simplicity, but they are understood. How would we handle this transformer differential protection if the differential relay had only 2 restraint coils per phase, like this? In this case, we would have to parallel the CT from the third winding with that of the second. As long as the load in and out on all 3 windings balanced, this would be acceptable. But supposing we had to operate this transformer with the high voltage primary breaker open. In other words, the power supply into the transformer would now be from this 69 kV side to feed the outgoing 13.8 kV. If the secondary currents were perfectly balanced, there would be no problem. But as we know, there is always some error current, and this would pass through one restraint coil and then through the operating coil. In fact, now we have only one restraint instead of the previous 3. This would probably be insufficient, especially for a heavy through fault on the transformer. Hence, the reliability of the protection would be considerably reduced. For this reason, remember, CTs should not be connected in parallel, and each CT should be connected to a separate restraint coil. Here's another example of multiple connections to transformers. This single line diagram shows that the primary can be fed from 2 different sources through separate breakers. Similarly, the secondary can be fed to 2 different loads through separate breakers. In other words, there are 4 connections. We must have 4 CTs, and these will be connected to 4 separate restraint coils on the differential relay. By now, it must be clear to all of us that differential protection on transformers is not just a matter of installing a differential relay. The connection of CTs requires careful study, and remember, there are many different applications. Each installation must be studied on its own merit. You should try to obtain differential protection circuit diagrams for your own power system, and study these with the help of your supervisor. At this point, let's take a break, and then we'll come back and continue our study of transformer protection. For now, please switch off the tape and review this material in your workbook. In the last segment, we pointed out that the normal differential protection scheme will protect for ground faults, as well as phase-to-phase faults. This is because the relay is sensitive to the unbalance caused by the ground fault, as distinct from direct measurement of ground fault current. However, in some cases, a ground differential relay, 87GD, is connected to measure and operate on zero-sequence ground fault current. In an earlier tape, you will remember we discussed the application of this relay to generator protection. Another typical application is with the distribution substation transformer, where the high voltage side is connected in delta, protected by fuses, and there are no CTs available. The secondary side of the transformer feeds through a breaker into the substation bus, from which various feeders are tapped off. The secondary side of the transformer is Y-connected and grounded through a resistor. Let's now look at the three-phase diagram and see how the ground differential relay is connected. If there is no ground fault present, then no current flows in the secondary circuit of the CTs. If an external fault occurs, say on line C, then the zero sequence current will flow through the CT secondary to the relay, but this will be counterbalanced by the same value of current flowing from the neutral CT. Therefore, no current will flow through the relay operating coil. But if there is an internal ground fault in one of the transformer windings, the current in that CT will reverse and be added to that from the neutral CT. This current will flow through the differential relay and it will operate. Quite often with this arrangement, an additional time overcurrent ground relay, 51G, is installed in the neutral. This acts as backup for the transformer ground differential and also as backup for ground faults out on the feeders. It must be correctly coordinated with protection on the feeders. The primary high voltage fuses may not clear for a low-level fault on the secondary winding or the secondary system. They are usually sized to protect against heavy short circuits in the primary winding. Operation of the backup ground protection relays will initiate tripping of the first breaker upstream of the fuses in order to isolate the primary winding. In our example, this would require tripping of this remote circuit breaker. One way of achieving this is to provide a communication channel between the relay and the breaker. This is known as a remote transfer trip signal transmitted over power line carrier or on a telephone circuit or microwave circuit. This method is quite expensive, and special care needs to be taken with the installation so as to avoid interference from outside signals which may cause inadvertent tripping. Of course, on large, high-voltage transmission lines, this method is used extensively, but it is not so common on distribution systems. One method of initiating the trip is to have the protection relay trigger a spring-loaded ground switch. This will apply a solid ground to one of the lines on the high-voltage side. This, in turn, causes operation of the ground relays in the remote station and so opens the breaker. Depending on system design, the ground switch could be three-phase or single-phase. Generally speaking, the ground switch arrangement is not often used on new installations. Instead, a circuit switcher may be installed on the transformer primary instead of a high-voltage fuse. This is far less expensive than a circuit breaker, but in return it provides very limited fault interrupting capability. If the fault current is low, this switcher will be quite capable of interrupting the circuit. If the fault current is above the circuit switcher's interrupting capability, this high-set overcurrent relay picks up instantaneously. This blocks the circuit switcher's control unit from operating and thus the circuit switcher from tripping. Then the remote protection at the substation will register a fault on the feeder and trip the circuit breaker. Another method of achieving ground fault protection for transformers is by the use of a directional overcurrent relay connected differentially. It consists of two units. The overcurrent unit's operating coil is connected across the line CTs. The directional unit has two coils, and when current flow is correct, it allows the overcurrent unit to operate. Now, for an internal fault, current will flow into the transformer from the feeders through the fault and circulate up the neutral. The circulation of CT secondary current is such that the directional unit picks up. Also, the two currents add in the operating coil and so trip the relay. Even if there were no backfeed into the fault from the feeder, there would still be sufficient flow of current through the relay in the right direction to cause operation. But what about a ground fault out on the feeder? In this case, the flow of current in the feeder CT will be reversed like this, opposing the flow of current through the relay. Well, at this point, let's take a break, and then we'll come back and summarize overall protection schemes for transformers. Please switch off the tape now and review this material in your workbook. In this segment, we'll be looking at some overall protection schemes for transformer installations. And this will also help us summarize and digest the information presented in the previous segments. This single line diagram shows a typical arrangement for a large transformer, say 10 MVA and over. Both breakers will be tripped in the event of an internal transformer fault. Let's look at the type of relays that are usually installed. Relay 49 is a thermal relay, and Relay 63 operates on gas pressure or gas accumulation. These so-called mechanical relays are normally included as part of the transformer construction. The thermal relay detects overheating of the oil or winding hotspots, which may occur as a result of continuous overload or perhaps an internal fault in the winding. The relay usually sounds an alarm and also operates the forced cooling equipment. The gas pressure relay, as its name implies, operates if a sudden rise in gas pressure occurs inside the tank. For example, if heat is generated in the oil by an electric arc. These relays are quite sensitive and can often detect a fault before it develops severely enough to operate the differential protection. Differential protection is the preferred method of protecting transformers against internal phase-to-phase faults or phase-to-ground faults. It is connected right across the transformer, including the primary and secondary breakers. Several backup relays are also installed. First, we have the overcurrent ground relay 51G, which is connected in the grounded neutral of the transformer secondary. This is wired to trip the primary breaker and serves as backup for a ground fault on the secondary bus and feeders. Often a second ground relay is provided to operate the secondary breaker, and this is set with a longer time setting so as to allow the secondary ground relay time to clear first. Overcurrent relays are often installed as backup in the primary and secondary circuits. This overcurrent relay will act as a backup for faults on the secondary bus or feeders. This particular transformer shows a delta-connected primary and Y-connected secondary, a very common arrangement. The delta-connected primary is not grounded. Therefore, backup ground protection for the primary is provided by this residual relay 50N, 51N. Alternate protection has a toroidal CT around the primary conductors to measure out-of-balance current, such as that which would occur in the case of a ground fault on the primary winding. On smaller transformers, it is usual to omit the primary side breaker for economic reasons. Typically, we may have many large and small distribution transformers tapping off a distribution feeder. The feeder will be fed from the substation bus through a breaker, but each distribution transformer will be protected by high voltage fuses only. Here is a typical protection arrangement for a distribution transformer feeding a small industry. Once again, the primary is delta connected and the secondary Y grounded. The basic protection is provided by overcurrent relays. A time overcurrent relay is installed on the outgoing secondary leads to protect the secondary winding against overload by tripping the secondary breaker. It is actually operating as a backup for any downstream protection on the feeders. The ground overcurrent relay 51G in the neutral will trip the secondary breaker in the event of a ground fault in either the transformer secondary winding or the connected feeders. As we mentioned before, a low-level ground fault on the secondary side may not be sufficient to blow the fuses on the primary. In fact, these fuses may not even blow for a ground fault on the primary, as the delta winding is ungrounded. The real function of the fuse is to protect the primary windings against a heavy phase-to-phase fault within the primary winding. But a small fault or perhaps persistent overload could go undetected and eventually damage the transformer winding insulation. Where this type of transformer installation is considered to be critical, differential protection should be employed using CTs in the transformer primary bushings and at the secondary breaker terminals. As the differential relay cannot trip the fuses, it must be connected so as to trip the primary source breaker upstream, as well as the transformer's secondary breaker. Slightly more complicated protection is required where two transformers provide parallel feeds to a common bus. Usually the bus is split by a circuit breaker like this. If this is normally open, each transformer will feed its own section of the bus. No additional protection is required. If one transformer is taken out of service for maintenance or inspection, its secondary breaker will be opened. The bus tie breaker will then be closed so that all of the bus can be fed from the single transformer, assuming, of course, that it has sufficient capacity. In some installations where uninterruptible power is required, the bus tie breaker remains normally closed so that both transformers feed all of the load. However, depending upon the configuration of the power system, this setup does have the potential for providing a path for backfeeding one of the sources. For example, line 1 and line 2 may not be fed from the same bus or even the same location. Consequently, there is probably some phase difference between them. In this situation, for example, line 1 may try to transfer load to line 2 through transformer 1 along the connected bus and back through transformer 2. This is a highly undesirable situation that may allow extremely high currents to flow through the system. For this reason, you will often hear the recommendation, never connect transformers in parallel. Adequate protection can be provided, as we see here. The directional overcurrent relay gets its reference quantity from the VT in the bus. The operating coil of the directional relay is supplied from both the CT in the transformer feed and from the CT in the bus. As long as the transformer is feeding into the bus, the directional relay will not operate because the two secondary currents are opposite to the polarizing quantity. However, if current is reversed and feeds into number 1 transformer's secondary, then the two currents will still be additive. But now they are in the same direction as the polarizing quantity, and the relay will trip, provided that the current is above the set point. Operation of the relay trips the secondary breaker, so now transformer number 2 will feed all the bus. Now at this point, let's extend our overall view of transformer protection to include reactors. This is because there are many similarities in construction and therefore protection is also similar. Generally, reactors are air-cooled or oil-immersed single or three-phase windings on an iron core. Where is the reactor installed? Well, typically in a grounded neutral to limit fault current, between buses to reduce magnitude of current flow, or shunt connected between line and ground to compensate for capacitance on long lines and prevent high voltage levels. As with the transformer, the main cause of failure is insulation breakdown, leading to phase faults, ground faults, and turn-to-turn faults. Protection is provided generally by differential relays, 87. Backup protection is usually by a ground overcurrent relay, 51G. Mechanical protection is usually installed using the gas pressure relay, 63, and the thermal relay, 49. Often reactors are connected directly to the line or bus with no breaker. Therefore, operation of reactor protection means that all remote breakers feeding the reactor must be opened. Once the reactor has been isolated by disconnects, the breakers can then be reclosed, but the system operator may have to take other steps to hold the voltage down. While we're speaking of shunt reactors, we can also think of shunt capacitors. As you know, these capacitor banks are connected between line and ground or bus and ground in order to raise the voltage at that location by supplying VARs to the system. The capacitors actually compensate for the series inductance in the line and are commonly applied throughout the distribution system. The capacitors are susceptible to serious damage if a heavy fault current flows. The casing may rupture with consequent spillage of insulating fluid. Each individual capacitor is protected by its own fuse. If several capacitors are isolated due to blown fuses, there will be some unbalanced current flowing through the neutral. This can be detected by the installation of an overvoltage ground relay, 59G, which will function to alarm the operator. Additional backup protection may be provided by overcurrent relays, 51, connected between the line and the capacitor bank. Okay, in this tape, we've looked at the most general types of protection schemes that are used on transformers, reactors, and capacitors. Make sure you check your own company installations and ask your supervisor to clarify any doubts that you may have. Please switch off the tape now and thoroughly review this material in your workbook.